Okay everyone, welcome to ELCM374's first presentation. This presentation is titled Data Communications. And first of all, before we got started, what I wanted to do is just kind of define a few terms and define a few things. One of them is, what exactly is an industrial network? Well, an industrial network is where we have two or more smart devices communicating over a common medium to share information and to work together collectively on a greater process or a greater task than can be performed or processed by a single smart device. Now, when we say smart device, what we're talking about is a device with a processor, and it seems like just about any appliance these days has a processor in it, whether it be a coffee maker, a fridge, a washing machine, a dryer, and so on. And once there is a processor available, all that would be required is a communications port or a way of speaking onto that network where it could share information with other devices in order to use information from each other to work on something greater. And so when it comes to a situation like this, we're going to learn about all the particulars that go into that connection, the speaking of the information between devices in terms of protocols and things like that. So that's really what we're going to cover in this course. So I just wanted to define a few things as well. So we talked about a smart device, and one of the acronyms we're going to learn of in this course and see it fairly often is an acronym IED. So IED stands for Intelligent Electronic Device. And otherwise you could just say it's a smart device. Okay. Another thing is when we're talking about networks, we're going to be talking about LAN and WAN, and use that all the time. So you may be familiar with this. LAN stands for Local Area Network. And WAN is Wide Area Network. So if you're looking at your home network at home, you have workstations, printers, and so on, all connected in your local area network over a layer 2 device like a switch. Oh, and when I say layer 2 device, I'm talking about the OSI model, of which we'll talk about later. But it's categorized as a layer 2 device to switch the traffic within a local area network. If you were to go outside of your local area network is where you'd be accessing wide area. So when we're talking about networks that cover large geographical areas or spread out over a long distance, they would certainly be wide area networks. They would need to go outside of their local connections, which are generally just communicated over local Wi-Fi or local copper connections. You'd have to access what's called a gateway to get outside of your local area network to access a wide area, and in doing so is where you would need to employ or bring in data communications or datacom to communicate that data over a wide area. So LAN and WAN, and then we're going to define specifically things like DTE, DC, and I'll just leave that for now. That's data terminal equipment, data communications equipment. We'll be defining that specifically in this presentation. So I think pretty much the rest of what we're going to look at will be defined within the presentation. But IED, LAN, WAN, DTE, DC is something that we're just going to get familiar with before we get started. Okay, so we're talking about data communications. And as we said before, an industrial network is defined as a group of smart devices connected in a manner that allows them to communicate information with one another and monitor and control a specific process or task. Such networks are sometimes referred to as buses. So that common medium, that common connection that connects two or more of these devices together is often referred to as a bus. So just like we have buses for power, we have buses for communications as well. So I'm sure you've heard of some of these terms or some of these protocols on the bottom of the slide here: field bus, Modbus, Profibus. Those are all examples of protocols used for multi-dropped networks for the organization or for devices to the protocol for devices to talk kind of on a party line on a bus. So first thing we're going to do is we're going to define industrial networks, and these industrial networks don't really vary a whole lot in terms of equipment used to connect them and or mediums used or the type of equipment used, but there is distinct differences between these networks, and therefore we categorize them, or they could be categorized into one of these three networks. The first one is a PLC network, and knowing that some of you have worked in the field and have taken, if not one PLC course previous to this course, maybe more, you know about PLCs. And when you have a logic controller that wants to communicate with another logic controller, you would have to network those devices. You'd have to have a network interface module of some sort, or a media access module to allow you to communicate between those two controllers, and this would be called a PLC network. So PLCs traditionally have been, you know, their strength has been discrete I/O and on-off control, sequence control. Certainly analog processes with PID and things like that have become more prevalent with PLCs. PLC is just a controller, a computer, right? So the capabilities of a computer, I think in some ways you could say, are pretty much limitless. So you would say that would be the same thing with a PLC. The thing is with PLC and some very sophisticated analog gas processes, even though I would say hardware-wise they'd be capable of handling it all, they don't have the proper approvals to do that, and this is where we'd have to have something like a DCS network, which has the proper safety approvals to be used in that environment. So that's the next thing we're going to talk about, is DCS, which stands for Distributed Control System. DCS is primarily analog I/O, PID loops, variable control type of network. So it's going to be used in things like water treatment, boiler systems. It's going to be used in gas plant situations and stuff like that. So it's a very fast resolving process that will take varying inputs and perform all sorts of PID calculations on those to provide variable output control. And there could be several different controls within a loop, and certainly many variables being incorporated in that loop to resolve a given output. So the thing really about DCS network is that it is process focused. If you look at the network itself and how it's designed, it's meant to be all about the process. So whatever it's doing, it's all about that. Any kind of communications or talking outside of its local area network is low priority. It's basically, if you want to ask me about anything about my process, like one of my variables, whether it be pressure, temperature, whatever, it's going to be low on my priority list to offer that up to you because I'm so focused on the process. So that's kind of one way of looking at it. When it comes to the SCADA network, and SCADA stands for Supervisory Control and Data Acquisition, and there you go. There's a hint for your first quiz question to define what the acronym SCADA stands for. That's Supervisory Control and Data Acquisition. So when it comes to the SCADA network, it looks at status values within its network as discrete I/O, on-off statuses, on-off control. It looks at analog values, a few analog values of voltage, current, temperature, pressure, data collection, like trends of a changing analog value over time loaded into a table and collecting that as data. So when it comes to the SCADA network, what is really important to understand is aside from what we talked about in terms of DCS, is that one thing that really separates it from DCS is that it's only a few points that are being monitored and controlled, and but it's a wide area network. SCADA network is distributed over a large geographical area, and so it's pulling in a few points, not a lot of points, but it's pulling in a few points from remote locations over a large area and displaying them to a central master, of which in most cases in a SCADA network there's not much automation going on at the wide area network. Everything's being monitored by operators and engineers, and through the HMI they vary the process. They make decisions based on generation, switching, load shedding, and all that when it comes to the electrical power grid. So primarily the big difference is the DCS being local area network, extremely process focused, and the SCADA network being wide area network and communications focused. It's all about retrieving that data from a large area. So just to review there, PLCs typically discrete I/O, on-off control, can be fully featured for communications. So in a PLC shelf, you could have all different communications modules and fully feature it for communications. And in that way, and a lot of times PLCs are being used in the SCADA environment as an RTU because of their flexibility. You can just fully feature them for communications, and then they'll do all the communications like an RTU in a SCADA network. And RTU stands for Remote Terminal Unit. So there is more PID and LAN/WAN communications coming into PLC networks, because again, that's where I see the PLC being so flexible and versatile. It can, really be customized to work in just about any network. So DCS is distributed control systems. Again, just about exclusively analog I/O, and it's really all about the process and a speedy resolution of an output based on variable inputs. So it's all about the process and the speed of resolving that process. So within a DCS network, there's smart devices running apps. So it means that within that loop, a controller has a local application running on it too, which can be monitored and controlled through the interaction of the DCS loop. And furthermore, you can upload new programs and so right over the DCS network. So Yeah, within we're just going to say a DCS network is a smart device or has smart devices running apps that communicate over a local area network to prioritize, like we said, the process. So communication to a wide area network is very low priority and often doesn't exist. Um, and so when we look at the DCS network, I sometimes give the DCS network the analogy of a ditch digger with his head down, focused on digging that ditch. And if somebody comes to talk to him and ask him how it's going, or how much does he think he'll get done, and or this or that, that's very low priority. He's kind of like, leave me alone, I've got a job to do here, we'll talk later. And that's sort of a way of thinking about DCS. Communications is very, very low priority. So then when it comes to the SCADA network, it's kind of the opposite. It's that model upside down. As far as the SCADA network goes, it's all about communications. It's all about talking, you could say. And that is that the SCADA network is designed to retrieve information by communicating. And really before SCADA networks came on the scene in wide area networks, like for electrical and gas distribution and all those things. All of this was looked after by central engineers and operators getting on the telephone and calling up these remote manned locations and talking to the site operator and collecting data that they went around and looked at the instrumentation and recorded values and recorded statuses and things like that, and also called in to report alarm situations or values that it had exceeded thresholds. There was all this communication that occurred basically by telephone and by operators and engineers communicating that way. But of course that was replaced by something more automated and 24/7, and this is where we ended up with these SCADA networks. But basically what we're saying is communications is huge for a SCADA network. It's all about talk. So just like it says here in the third bullet, data communications is of utmost importance to the SCADA network. And based on that is really why we are taking some extra time to look at that today. So SCADA provides monitoring and simplistic control of processes that are distributed over communities, towns, cities, and provinces. So it's wide area. Central Communications Master clients call upon RTUs for information and control of devices. So another acronym is AESO, Alberta Electric System Operator, and they look after they monitor and supervise and control all of the generation, distribution, and transmission of electricity in our province. And so if you were to connect to our grid, you would be required to provide certain SCADA variable data to AESO so they could look at what you're doing in terms of generation and what's online and what's offline, and they could make choices about load shedding and all that kind of stuff. So when we have central engineers at SCADA looking at all of that data has been gathered by data communications connections to provide them with all the SCADA data to make a responsible decision as to how to control the grid. So just like we said, communications is a big deal as far as SCADA goes. So in this slide here, this is where I just kind of used maybe simple analogy to see if we could kind of get an idea of how it's the function of these networks that determines whether they be classified as DCS, PLC, or SCADA. So in this example, at the top I've got, let's say at your main residence, your home, you've got a network connected that allows you to, via a cellular connection, see your car, whether it be downtown or in another city, or even just in your driveway. It allows you to, via cellular connection, interface with the car alarm module to see if on the left-hand side of the slide here, you could monitor the locking and unlocking of the doors. You could monitor whether the engine is running or stopped, your cab temperature, whether the heat or AC is on or off, and in turn you could control that. So you could lock or unlock the door, start or stop the engine, turn on or turn off heat or AC. So that would be a wide area network accessing that car alarm, no matter where it is, to retrieve a few points and to control a few points, and look at it, get a snapshot of what's going on at that remote site, being your car. Well, at the car itself, or at the vehicle itself, inside the engine compartment, there's another industrial network in there, made up of smart devices working together in a loop, and they're looking at analog values of airflow, fuel flow, fuel pressure, temperature, RPM, exhaust gases, etc. All of those variables are used to maximize the efficiency of that engine. So it's all about the process there for that network. So in that vehicle, there's actually two network modules. There's the car alarm interfacing to the wide area, and then there's the internal or local area network looking after the engine itself and prioritizing the efficiency of the running of that engine. Now, there could be at times values from this network being brought over to this network to add it as a variable that's being reported back to your residents. Let's say part of what you wanted to know remotely was, say, your RPM. Well, that data could be brought over from that network by a data connection between the two networks to request RPM values to be reported back to the wide area network. So I think you're kind of getting the idea. You could have another remote location, like say your cottage. Instead of a cellular connection, you've got a connection over a telco internet, so a TELUS or a Shaw internet connection. You've over copper and or cable, you've got a connection to your cottage. And at your cottage, you're bringing up some streaming yard video from a camera. You're looking at the temperature, whether the heat's on or off, whether the doors are locked, things of that nature. And you've got another drop of where you can monitor a few things and control a few things. So if we were to look at this, my next question that I would usually pose in a face-to-face class is, if we were to look at this network right here. So if we were to look at this network right here, that's involving the vehicle's engine and the network and its priorities and definitions in terms of a local area network, how would we define that specifically if we're looking at defining between SCADA and DCS? Well, I think you could understand that this is the one that we would say is most like the DCS system based on what we talked about. So DCS network here, then of course the whole network here that involves all these devices in a wide area network is one that you would say is simulating the SCADA network. Wide area, multiple datacom, right? In one case it was cellular, the other case it was ISP over an internet provider to provide your connection. And it was a wide area with a few points being monitored and controlled remotely, and then with a central operator at a master control center, which would be your home, being able to monitor everything on an HMI and make choices or changes to the process or the system based on the data that are being gathered. So that's the idea of that analogy there, to give you an idea of a SCADA network and DCS and so on. Okay, so data communications is all about moving data, and data is defined by moving data from point A to point B using specific signal conversions and mediums for long distance data transfer. And this is kind of a really important part of when we're talking about data communications. When we define data comm specifically, we should understand the difference between data comm and data transfer. And so we'll talk about that in a minute. And I'm sure you guys know this, but data is always ones and zeros, so it doesn't matter whether you're watching a movie, downloading a picture, or watching TV. When it comes to digital communications, you're always really viewing what's the result of ones and zeros being communicated and then decoded or interpreted by different software programs and applications to do their job, to display a picture or a video or whatever. So all internet traffic is ones and zeros, and all IP addresses are ones and zeros, and so on. So it's good to know that as well. So the distance over which data moves within a computer itself, or within a tablet or an iPhone or so on, can be like minute, a few thousandths of an inch, and there's ones and zeros moving all over the place within a computer or a phone or a tablet, and that's generally referred to as just data transfer. And it's only when it's communicated outside of that device that it takes on the term datacom. So if now you've picked up your phone to make a phone call or to access the internet, then your phone had to access its media access port in order to do that. So maybe it would be a cellular or wireless or radio frequency connection that it's accessing to get outside of its local area and to move to a data communications as opposed to a data transfer. Hopefully that makes sense. So when we have a short distance to transfer data, then we can just keep our ones and zeros as a voltage signal. We can have a high voltage signal corresponding to a logic 1, a low corresponding to a logic 0, and it's the detection of that voltage level that will indicate the information. Is it 0 or 1? Is it yes or no, true or false? But of course what we're going to find is that could we communicate those ones and zeros, or transfer those ones and zeros over long distance in that way as an electrical signal of highs and lows? Well, certainly the answer is no. So it says here, we are not very concerned about the type of conductor or the connection or the analog characteristics of that connection or that transmission line, because it's such short distance. So if we were to think of just connecting a voltage signal from a data source to a data destination, and for those of you who completed the ELTR 232 electronics course when you went into digital and you were using those trainer boards, you connected ones and zeros like this from one gate to another on that trainer board to maybe a maximum of 2 feet, and you just connected it over a couple of copper wires, and that worked. We had a voltage input signal being detected by the gate that was receiving the signal, and it was easily able to interpret that voltage as between 0 and about 1 volt, and between 2 volts and 5 volts to retrieve the information, to interpret the ones and zeros. The thing is, if you were to string out that copper connection over many feet, as an example here, 200 feet, what leaves as this signal ends up being received at the destination as a signal that is much harder to interpret based on the characteristics of resistance, noise, capacitance, and inductance changing that signal. When it comes to resistance, it's going to affect the amplitude of that signal, and it's going to drop what may be 5 volts down to a lower voltage down in this range, which is undetermined and hard for the other end to distinguish whether it's a 1 and 0. And then you have the frequency affecting characteristics of capacitance and inductance that naturally occur in that connection, causing a distortion of the wave, and you end up with, instead of a nice square wave, you end up with more with a sine wave type of signal being received. And of course this is the problem, because it means that the information can be completely lost over long distance on a connection such as that. So just like it says here, often data must be moved outside of a PC terminal or a smart device and transferred over long distances, and certainly that's always the case with SCADA. As the distance between the source and the destination increases, so do the problems. Resistance, inductance, and capacitance affects the waveform. Electromagnetic interference causes noise on there. So noise and distortion cause the information to be lost completely. So this is an example here, like I showed, transmitted signal, nice and clean, easily determined as 0 or 1, and then it starts to distort, and there's attenuation and losses, and problems occur where there's errors and complete communications or information lost. So generally speaking, data communication describes when data is transferred outside of a local area, outside of a PC or a terminal, or and passed on to another PC or terminal or local area network. The distance could be simply a few feet, or it could be kilometers, as it would be in most SCADA networks. Is there'd be a data connection covering kilometers, if not thousands of kilometers. The goal of any data communication system is to provide the highest possible transmission rate at the lowest possible power with the least possible noise and data errors. So just like any other properly engineered or designed system, it's designed to be the most efficient, and really that's what we're talking about here. And to put it another way, to provide the highest data throughput, and really that's a term that means moving the greatest amount of data in the least amount of time, is what highest data throughput means, with the least errors. So that means there's we're looking for virtually no errors, and consuming the least amount of energy, so being very power efficient as well. So when we're talking about data communications, there's all sorts of unit values for 1s and 0s that we talk about. Certainly a 1 on its own or a 0 on its own is called a bit, but being that that's a very, very small unit when we're talking about data communications, when we're talking about gigabit Ethernet or things like that, is we have other units to describe it. So just like we have engineering prefixes to take very large numbers in engineering and express them as a smaller number based on a prefix of giga, mega, tera, and so on, it's the same idea here. So I'm sure you've heard of a byte. A byte is 8 bits, and then depending on these different protocols or operating systems, you will have other units or sized units that are called data blocks, data words, and packets. So packets are used a lot to describe a definite amount of bits or bytes in IP traffic or internet traffic, and data words are used to describe a group of bits or bytes as well. If you think as an example as a 32-bit operating system in Windows and a 64-bit operating system in Windows, what's the difference? Well, in a 64-bit, they're using 64-bit data words to communicate and perform the process, and the other, they're using 32. Well, obviously with more information in the 64, you can get essentially more work done within a same amount of time. So data blocks, when we look at Modbus and DMP, we'll be able to see how data blocks and things are set up for those protocols. So looking at communications modes now, it doesn't matter whether you're talking about voice communications or digital communications. There's 3 different modes you could be operating in. The first one we're going to look at here is one called the simplex channel, and that's where you have one transmitter transmitting in one direction to a receiver. There's actually no information or communications back from the receiver back in the other direction to the transmitter. It's one direction and one direction only. And it could be several receivers, or it could just be one receiver set up as a simplex, but in most cases for these simplex channels, it's one transmitter sending to multiple receivers. So an example of that would be like a digital TV station, a digital radio station, satellite TV. Satellite TV is a simplex system where the satellite broadcaster is uplinking to the satellite, and then you're receiving the downlink from there for your satellite receiver. So that's an example of a simplex channel. We have next a half duplex channel, and that's where data moves both directions, but it's a take your turn type of connection. So you can only have one person talking at a time. And so when we think of an Ethernet connection, Ethernet connections can be either configured as half duplex or full duplex, and most of the time it's the equipment on either end that determines whether it's half or full. So when it comes to a half duplex system, what's something we could think of that kind of demonstrates that would be your walkie-talkies, like your push-to-talk radios. Once you've pushed to talk, you cannot listen. You have to release to listen, and there's only one direction communications at a time, but you do have the capability of communicating both ways. So that's a half duplex. And then lastly, you have full duplex, which allows simultaneous communications both directions at the same time. So the example we have there is cell phones, and so certainly your cell phone is capable of full duplex. You could talk and listen at the same time. I would say that just like in data communications, a cell phone is the cell phone itself, the connection is a full duplex connection, but the terminals are only capable of half duplex. So I would say when we say a terminal in a cell phone call is the person on either end, I would say the person on either end is only capable of half duplex, and so it's half duplex devices or terminals communicating over a full duplex connection, if that makes sense. So when we're looking at data transfer, remember this is where we're not communicating long distance. It's just within a device or a local area. You can communicate in 2 ways, and that is one being serial and the other being parallel. Nowadays, just about every connection, whether it's local or long distance, is serial. If we take as an example, as a little local area network, you could say, on your workstation at home, it would be a USB network, which is a serial network connecting all the devices serially. Something different than that is our parallel connection, and there's not many parallel connections around anymore because of the kind of processing speeds made it, I guess you could say, not necessary. But we still have to understand there's 2 ways of making that connection, as a serial or parallel connection. So notice how both these terms have the name serial in them, but if you look closer, you can see that the second one is not bit serial, it's byte serial. And byte serial is just another way of actually referring to parallel. So if we look at the first one, the bit serial, the example of a bit serial cable we've got here is an RS-232 full duplex connection. It means that over time, your ones and zeros would be transmitted or streamed down one of the data lines, if you think of it traveling down one of the data lines, and each one of the bits is read one at a time as it's received at the other end. When we're talking about a byte serial, which is actually parallel, what it means is you've got a separate data path for each one of the bits that makes up, let's say, the data word. And so in this case it would be an 8-bit word, because there's 8 lines, and each byte, because remember, 1 byte is equal to 8 bits. So that's why this is called byte serial, because there's 8 bits at a time being sent on 8 separate conductors or 8 separate data lines. And now you've got, instead of a, sorry guys, and now you've got, instead of 1 bit being received every clock pulse, you've got a full byte, or a full 8 bits received every clock pulse. So I think you can see, using the same switching rates or the same data rates from one to the other, that byte serial or parallel would move 8 times the data, or have 8 times the data throughput that a serial connection would. Like I said before, with the processing speeds and technology that's available today, you don't see as much parallel as far as peripheral equipment goes, like a mouse or a printer, things like that. Back in the day, parallel connected printers were very popular, but now with USB printers and stuff like that are pretty much everywhere. But when it comes to the backplane of a computer, the motherboard, talking to all the devices, it's all very local area, very within the computer housing. That would all be connected in a bus, and it would be connected as a parallel bus to move large amounts of data from the motherboard to the devices very quickly and efficiently. So that's what you have going on there, is another byte serial or parallel connection there. Notice how it's saying it's half duplex, so that means there's a protocol going on over that connection, so that there's not multiple devices obviously trying to access that at the same time. You know what half duplex means now, right? Take your turn type of communications. So when it comes to data rates or data speeds, one of the ones we're going to be get familiar with, because we're going to be looking at a lot of asynchronous serial connections, is baud rate. Now, I think probably what the most important thing for us to take away from this is baud rate doesn't equal bit rate. A lot of people will say 2400 baud is 2400 bits per second. Well, actually it's not. And baud rate is actually defining the number of electrical transitions in 1 second for a specific connection. And NRZ stands for non-return to zero. And it depends on the type of encoding method that's used for the data as to how you could translate baud rate to bit rate. But ultimately, I don't really think that's important information. I think really what we want to concentrate on is that baud rate is simply indicating a data rate, or the speed at which data is moving, and a bit rate's doing the same thing, but they're not equal. So there's no doubt 9600 baud is a faster rate than 48 or 24 and so on, but they're not actually equal to bit rate. So when it comes to today's connections, like Ethernet and say your internet service provider like Shaw or TELUS, they're going to give you a bit rate to indicate your data rate or your data speed. So I'm sure you've heard of, Shaw or TELUS guaranteeing 25 megabits per second download or something like that, right? So that's bits per second download. And then lastly, we have something called a character rate. Now this is from older data days for sure, where instead of evaluating something like how many bits can be transferred, it it's a little bit more of a useful information, because it's saying how many characters per second are transferred. If I have a different size character, that's obviously going to be related to my bit rate, but what's more meaningful is probably the assembled characters and how fast they're being sent per second. But again, character rate and baud rate are both kind of evaluations of data speeds that you'll probably find are not being used as much based on industrial Ethernet and more modern connections. But baud rate is definitely something we will be looking at when we go into the lab and we do some of our asynchronous serial connections like RS-232. Okay, so in a data communications link, we have 3 elements. So you can kind of think of it like a electrical system elements, where you have a source, a transfer medium, and a load. Without one of those elements, the system wouldn't work. So it's the same idea in a data communications link. In a data communications link, you would have a DTE, or a terminal, or sorry, you would have at least 2 terminals. You would have data communications equipment, DCEs, and then means or ways to connect them as a transmission medium or a data channel. When it comes to the terminal, it is our source or our destination for data. So remember, I used that analogy of somebody talking on the telephone, on the cell phone. If you are talking on the cell phone, you would be the source of speech. Your cell phone would be the communications equipment to send it out over that wireless medium, and then the cell phone at the other end would be the communications equipment to receive that wireless signal and translate it into a signal appropriate for the other end, which would be the voice that's being heard by the destination side. The person at each end would be like the terminal. The cell phone would be like the data communications equipment, and then the wireless carrier that connects the two would be the transmission medium, if that helps at all. When it comes to a data terminal, the signal for a data terminal is always the same. It never changes. So we're always going to have a signal like this for a terminal. It'll always be highs and lows, ones and zero, a voltage of low and high representing information. That's what's going to be specific about a terminal. Its signal will always be the same. Doesn't matter whether it's an RTU, a PLC, a PC, or any IED or smart device. Its signal, its information is always going to look like this. So it's going to be sourcing this data or receiving this data. A terminal is always going to be either sourcing or receiving that signal. When it comes to the DCE, however, its signal that's being transmitted over the medium or received over the medium is going to be dependent on the type of medium. So if it's a fiber optic connection, that means the DCE is going to be sending out a light pulse and receiving a light pulse at the other end. If it's wireless, it's going to be an RF signal. If it's a telephone modem, it's going to be a tone, or it's going to be an audio tone. You could actually hear the tone for a 1 or a 0 based on it's within the audible band. So that's what we have going on here, is DCEs that are telephone modems at each end, and there's a audible signal that's being communicated off this these phone lines that sends a frequency in one direction that's slightly shifted based on a 0 or a 1, and then it sends a frequency the other direction that is that's shifted based on a 0 or a 1 going the other direction. So this is where tones are used, but the DC, or the data communications equipment, is has an output signal for the communications medium that's specific to what type it is. So this is where DCE can be working with all sorts of signals, whereas a terminal is only working with one type of signal, and that's the highs and lows, ones and zeros, like you see here. Okay, we'll go into that in more detail when we look specifically at modems and modulation techniques and so on. But this is what the job of the DC is to change the highs and lows, or the electrical signal, from the terminal into a signal that's appropriate for the transmission medium. That's its job. It does signal conversion. And one way to think of a DCE is a to D converter and a D to A converter. In the transmit direction, it's converting digital information to analog, whether it be light, radio, and so on. In the receive direction, it's converting an analog to a digital signal to pass that on to the receiving or destination terminal. So the data channel, like we said, is the pathway over which the information is being shared between DCEs. So that could be a physical wire, as in a copper Ethernet connection or a telco copper connection. It could be something that doesn't have any guided and or physical presence, maybe you could say, as a wireless radio, a laser, or a fiber optic light source, and so on. So information originates from a signal source, however there may be more than one destination. Whoops. So in our previous example, we saw there was a point-to-point connection between those two modems, but there could be a truly bus connection where you have a multi-dropped, and that modem is communicating with several other drops or DCEs in a multi-drop scenario. Okay, so here's where we have essentially the point-to-point system, but in more general terms. And so we have a DTE on either end as a terminal. That's the source and the destination, right? So over here, if this is the destination, we've got data flow in that direction. It's across a medium, could be radio, copper, fiber, and the modem could be a cellular modem, telephone, or Ethernet modem. Okay guys, so just back at the presentation, just took a bit of a break there. So we left off here, we were looking at this connection for a datacom system with DCEs and DTEs and so on. What I wanted to do here was just kind of quickly look at how practically this is done in terms of some of the more specifics. So in this example, I'm going to use the telephone modem. So here we have two DTEs that want to communicate datacom, and so we've got the DCEs involved, in this case the telephone modem, so this would be modem. And I'll tell you guys is that just about all the time a DCE is going to carry the name modem. So if this is a fiber optic line, you'll see fiber optic modem, Wi-Fi modem, telephone modem, Ethernet modem. They're all examples that include the name modem. So if you see the name modem, you definitely know you're talking about a DCE of some sort. So in this case, we're talking about the telephone modem, and the job of the DC or the modem is to take the digital signal, of which you know is always the same for a terminal, and change it to a signal appropriate for the transmission medium. And in this case, it's a telephone line. And so the standard telephone line has a frequency response from 0 hertz to 4 kilohertz, so 4,000 hertz. So that would mean that any of the information of ones and zeros that was communicated between these two DCEs would have to somehow use that that bandwidth, that frequencies, those frequencies to send the information, and sure enough, that's the case here. Now, this telephone modem's medium is a full duplex medium. So you may be asking, how is that done with a single telephone line? How can we have two devices talking simultaneously over a single line? Well, the way it's done is with frequency division. So we just look for an audible carrier to send the information this direction. So let's just pick a each and every baud rate has a unique carrier designation. I don't remember what they are, but let's just say, pick for example, a 2175 hertz carrier here. Okay, I know that's one of the carriers, I just don't know which one it's for. But that falls within the frequency band of 0 hertz to 4 kilohertz. And this is going to be the carrier used to move data as a frequency between DCA and DCEB. That carrier can be modulated by frequency as, say, 2150 for a logic 1, and let's go 2125 for a logic 0 as an example. So the frequency shifts between two frequencies for 0 and 1, and that carrier is what carries those zeros and ones to DCEB. And that would be an audible tone you could hear. Well, the other direction then, which is simultaneously carrying information from B to A, is going to be another carrier. So let's say it's going to be 1550 hertz. Okay, so now it's got frequency separation or frequency division from the other carrier that's moving data in the A to B direction, and this is going to be the carrier over the same single channel, over the same bandwidth, moving data the opposite direction. So let's say it's 1550 carrier. So let's say 1500, 0, and 1575, 1. I'm just pulling something out of a hat here, but you get it, that the frequencies being shifted between 0 and 1 to send data in this direction. And in that way, with those tones on the line, the detection of a 2100 frequency is being detected by B, and a detection of a 1500 frequency is being detected by DCEA in order to retrieve the data. And that's the way you can have full duplex communications over a single channel. In the example of a telephone modem, that corresponds to its frequency division. So one example I use just to kind of, something you can maybe relate to is if anybody can remember dial-up telephone modems to accessing data connections. Maybe it was back in the days of internet, and back when you had to access the internet that way, or even just a data connection for maintenance on a relay or a PLC or a remote device. But if you remember, the whole connection started out with this beep bop boo boo shh, and then you'd hear that part. And when the initial tones that you heard, that beep bop stuff going on, that was the two modems talking to each other through tones and deciding what baud rate they were going to connect at. Once they had done essentially a couple of different pings and looked at the results to see which baud rate was the one to work with at that time, they would basically, through those tones, agree on the baud rate to connect that, and they would proceed with the connection. And when you heard that sound, that was all the frequencies of, say in this case, the 2175 changing between 1 and 0 and the 1500 changing between 1 and 0, all mashed together, and what you heard was that kind of or noisy sound, and that was data being transferred, and that's when your connection was established and you started to move data. And so that's just an idea of how this this telephone modem works and how these DCEs work in that situation. So the next thing we're going to talk about is defining a serial data link as a synchronous data link or an asynchronous data link. Now, the first one we're going to look at is the synchronous system. Now, the thing is about a synchronous system is I really don't think any of us who go out to work in the field on any kind of datacom connection would be working with a synchronous data connection. This would be something that your major carriers for data would be exposed to, like say TELUS or Shaw or things like that, because This is for data trunks. This is for what's sometimes called big pipes for data. They're carrying huge volumes of data between major centers. So in the example I'm going to look at is an example of, say, a fiber optic link between Calgary and Edmonton. So this is where where we're talking about major ISPs would be working on connections like this. So and when I say ISPs, I mean internet service providers. In synchronous systems, separate channels are used to transmit data and timing information. So there's a separate timing channel from the actual data. The data is just streaming continuously as data, but in order for that data to be interpreted at the other end, it needs to include that synchronization signal or those clock pulses or that timing channel to know when exactly to read that stream of data for a 1 or a 0. And this is what's called a synchronous data channel. And so the receiver will read the data only when told to do so, or when you say only when it receives a clock pulse or the edge of a clock pulse to say, okay, now's the sampling time for that data. So in this example that I'm looking at here, this is what we're going to consider to be the synchronous data link and this fiber optic connection between these two major centers. So this would be our data trunk, and it uses the word trunk because it's carrying many circuits over one pipe, many circuits over one connection. So as well as having the data signal, which is the 1s and 0s with the meaningful information moving back and forth over this fiber optic connection, you're also going to have this clock signal. Now, many times these carriers have their own central clock that is distributed across their whole network and generated by themselves, but a lot of times it's timing information that's taken from external sources. So as an example, you could use our power system, our grid, and the 60 hertz frequency that would be synchronous across the whole province. You could use that as to derive your clock signal. So sometimes it's not actually in the communications at all. It's at each DTE, it's a separate connection to a clock. But a lot of times it's another clock signal that's sent alongside the data, and it's received as a separate connection and transmitted as a signal from one DTE to another. But, you know, like I said, you could use the 60 hertz power system for synchronization. You could use something called the iRig system for synchronization, or other internet-based type synchronized clocks. So at the end of the day, what are we really trying to say? For a synchronous data link, there's not only the data connection, but there's a clock signal to go along with it. And that's because this connection is all operated under something called time division multiplex. So it's the actual position in time of any of the bits that determines where they're going and where they're to be routed. So clock signal is so important in the synchronous system, because if you actually lost this clock signal, your whole system would be down. Without the clock signal, you're not receiving data. Your time division multiplex is lost. And then, of course, because of the clock signal being so important, what there is clock redundancy. So what I mean by that is, with that clock signal being sent, what there is a hot standby clock signal running right alongside it, such that if you lost one of the signals, it would just hot standby transfer over to the other clock signal. Yeah, okay, so hopefully that helps you understand the synchronous data link for major data trunks. Okay, I want to go to the next slide. Okay, well, let's try that. I don't know why I couldn't get that. what we would all be working with is asynchronous serial data connections. These are connections where the actual synchronization that is necessary for any data link is actually embedded in the same stream or serial train of bits. It's the synchronization is right in the data. So this is called asynchronous serial data. So serialized data is not generally sent at a uniform rate. In the synchronous system, it's a uniform rate, and it's all being sampled using the clock signal. But in the asynchronous, there's bursts of data, and then pauses, and bursts and pauses. And so in order for the receiving end to know when to read the bits coming in, it's got to know when something called the asynchronous data frame begins and when it ends. And this is all determined by its asynchronous formatting or configuration and the synchronization bits that are right in the data frame signal. So what is the data frame? It's a character or a meaningful string of bits which is framed by the synchronization bits, and specifically the start and stop bits. So the stop and start bits provide the synchronization in the frame. They tell the receiving end when to start. They tell it when the last information bit has been received and it's time to stop. The start bit is the attention bit alerting the receiver, and it's always a low. So the data channel is when it's idle or paused, or there's nothing, it's waiting for a next information bit to come. It's in what's called a marked idle state. And this means that it's a high when it's not sending data. And the start bit is always a logic 0 or goes low. So here's where we see an example with data versus time, or the voltage signal representing data versus time. So notice here, this axis is labeled in time. So this is actually time 0 here. This happens first at time 0, and this is time that's getting newer, I guess. So you could say this is going back in time. If you go to the left, you're going back in time. So if we look at this channel originally, it's in a marked idle state. So it's in a high voltage state when there's no data going on. And there's a reason for that. That's so that the receiving end, when it detects voltage, it knows it has a connection to the other end and that it's not in a communications fail. So with a marked idle state, we know we have a connection to the other end. It's as soon as the data channel goes low, like it does here, that the receiving end knows that it's a start bit. So the receiving end sees that low going signal and says, okay, now it's time for me to start reading the incoming signal, and it waits the appropriate amount of time and starts sampling the signal at every bit. So here it would sample each one of those 8 bits essentially in the middle to determine whether it's a low or a high. And even though this looks like maybe that's all highs, it's not actually all highs. It could be either a low or it could be a high. So we'll just show it as if it was alternating here, right? But the sampling occurs on the middle of each bit, and then the receiving end can interpret that character as an 8-bit character here as the meaningful information. But what was this, that's over here. What was this bit and this bit doing? They were providing synchronization. They were providing synchronization between the two ends. And so what's really important in this connection is the fact that each end has to be programmed for the same data rate. And if they weren't, if they weren't both programmed for, say, 9600 baud, one end would be sending at 9600 baud, the other end could be receiving at 4800 baud, and it would be only sampling every second bit based on its understanding that it was a slower baud rate. So this is where we need to understand that in these asynchronous serial connections, each end has to be programmed for the same baud rate. And remember, I talked about that dial-up telephone modem where the first thing they were doing was agreeing on the baud rate. You can imagine if they didn't make that agreement, one would be sending at one, the other wouldn't know what the baud rate was and would be sampling at the wrong times, and there'd be no meaningful information exchange. So I'll talk about this more in class, and we'll talk about it more in lab class when we look at our first lab on RS-232. But to begin with, I just wanted to give you kind of an overlook at the asynchronous data frame and the how the start and stop bits provide that synchronization that in a synchronous channel is looked after by the separate clock signal. So couple of things to look at here. One of them is, if you look at this very first bit, it was actually labeled LSB. Now, no matter what networking course I've ever taken, whenever we've looked at asynchronous data link, a quiz question that's always come up is, what is the first character bit that's transmitted in an asynchronous data channel? And always you're looking for the answer LSB. It's the least significant bit, because remember, we're going back in time here. So the first thing that was transmitted was the LSB, and then it transmits all the way up to the last bit being the MSB, or the most significant bit. Now that's important, because if you've got that series of bits and you don't know which is LSB and MSB, you won't be able to properly interpret it to know what the meaning of that character is. Yeah, okay. Now I will address parity right now. Most data connections now don't include parity for error detection of this data. And really it's because now the terminals on either end of this asynchronous connection are smart enough to detect errors without the use of parity. And so when it comes to connections that we're going to find in the lab, you're going to find that just about every connection you're going to configure is going to be something called 8N1. Okay, so what the 8 part means is it's at an 8 data bit character. What the N means is that there's no parity. So that is to say, this bit that's shown in this frame is not there at all. There's no parity. No parity. And then lastly, there's one stop bit. So the number of stop bits can vary. The number of stop bits can vary. You can have one stop bit, two stop bits, or 1.5. But primarily this is what you're going to see for every asynchronous connection these days. 8 data bits, no parity, and one stop bit. And like I say, the reason why we have no parity is because the terminals on each end are intelligent enough to find errors in the data without the parity bit doing that themselves, right? So basically what there is as an example, if we're moving Modbus data over an asynchronous serial data link, the Modbus protocol itself has something called a CRC data error detection code embedded right in the data. So it doesn't make any sense to be using parity in the connection, because the protocols that are being operated by each terminal are detecting errors in that way. So you'll see all connections now are no parity. We could talk about parity here for a second though, and when we're talking about parity, we have two types of parity, even or odd parity that could be programmed for a connection. And what it does is it simply adds another bit to the data frame that is indicating essentially the number of ones in the character. So if we look at this example on the bottom, this is an even parity detector or an even parity generator. So at one end you have a generator, at the other end you have a receiver to receive the parity. If we look at this data word going out, we can see we've got 1, 2, 3, 4 ones in that character. And because we have 4 ones in that character, that means it already has an even number of ones. So because it already has an even number of ones, the parity bit that will be sent will be 0, because it doesn't want to make the number of ones even. It's already even. So it sends off that parity bit. Now at the other end, when this is received, it receives all of this data. It receives the parity bit. It does its own even parity generation, and it compares its calculation to what's received. And if it's the same, it says there's no errors. Well, down here there's an odd number of ones, so what did it do? It added a 1 to make it even, and at the other end it receives the 1, it receives all this, it does its own parity generation and comes up with a 1, compares it to this one, and says that there's no errors. Now I think you can see how this would be a very low level and could be very poor error detection based on the fact, what if there was 2 errors in a single character? You wouldn't know that because you would get the same result. So parity, you'll find, is not used anymore. It's something that was used a long time ago based on the fact that the devices aren't intelligent like they are today. Okay, so I'll leave it at that. So here's where we're going to talk about RS-232. And when it comes to RS-232, this is still a very common, robust, and heavily used connection in industrial networks. Just about every Schweitzer relay that we're going to look at in the lab is going to have an RS-232 port. Some of the newer relays are definitely going to have Ethernet ports as well, but all of these industrial devices are just about all still going to have RS-232. It's still a very respected, used, and robust and reliable connection. So way back in its day, the RS-232 connection was a connection designed to be used between a terminal and a DCE, or a terminal and a modem. Originally it was 25 pins. So because the terminals or devices were a lot dumber back then, or whatever, or less sophisticated, they required more, you could call them traffic signals or handshaking signals. There'd have to be signals involved in the connection that said, hey, wait, stop sending data, my buffer is full, I need some time to process it, or I'm not ready to receive your data yet, I'm still initializing, or whatever. So we had all these carrier detect, request to sends, terminal ready. These were all these additional signals that were connection between the two devices, the terminal and the modem, or the terminal and the DCE, that were called handshaking or traffic signals. You could think of them as to direct the data traffic between the two. Nowadays, like I said, with smart devices and buffers that are capable of processing data far beyond an maximum asynchronous serial rate for RS-232, we're really down to only 3 pins or connections for these smart devices over a 9-pin connection as opposed to a 25-pin. So I often tell my students, if you were to go out in the field after getting a job and having to work with a RS-232 device, if you found it to be 25-pin, it probably means that equipment is from way back in the 70s or 80s, and it's time to talk to your supervisor about upgrading your equipment or getting a new piece of equipment. it kind of is real telltale of its age. So nowadays, like I said, 3 pins are the minimum and are enough for most, if not all, applications of RS-232. And so this is what's called a 3-wire RS-232 connection. Now the thing is you won't be able to reduce this 3-wire connection anymore, because these particular connections are absolutely necessary. So you can't reduce it anymore. And that is transmit data, receive data, and signal ground. So you need a path for data to move one direction, a path for data to come back the other direction, and then a common ground for those signals, so what's called signal ground. Now back in the old days for 25 pin, that was the pins 2, 3, and 7. For 9 pin, that's 2, 3, and 5. So like I said, I wouldn't think you'd be looking at this at all these days. But 2, 3, and 5 for a 9-pin connection is a very popular 3-wire RS-232 connection. So basically the RS-232 connection could involve connection of all signals. It could include all data lines and all handshaking signals or control lines. But in most cases, like I said, it's just a 3-wire connection: transmit data, receive data, and ground. So here's an example of some of the handshaking signals. Clear to send, this is called. Request to send, data carrier detect, data set ready. These are handshaking signals that are rarely used anymore, aren't necessary for smart devices. So here we see an example of the 25 pin and the 9 pin. Notice how it's showing a connection between a DTE and a DCE, and you guys know what those are now. If it's a 3-wire connection for 25 pin, you've got 2, 3, and 7. And look at the names of 2, 3, and 7. Transmit data, receive data, and signal ground. Assuming you wouldn't see this because of how old it is, you'll be working with a 9-pin connection. Everything we have in the lab, for example, is 9-pin. You're looking at 2, 3, and 5. So look at 2, 3, and 5. So 2 is our receive data, 3 is our transmit data, and 5 is your signal ground. You could, in some cases, have additional handshaking signals like data carrier detect, request to send, clear to send in a connection, but you don't see that much these days. The manufacturer would indicate in their documentation if their device required some of those handshaking signals, and if it did, you'd have to include that as part of your cable map or your cable configuration to connect it and have it work properly. So that's what you see here. Now, if you look at each one of these examples, this is an RS-232 example from DTE to DCE. That's from a terminal to a modem. Each one of Hey, sorry, my video stopped there for some reason. But yeah, we left off here where we're looking at these RS-232 connections for DTE to DCE. This is what's called a straight-through RS-232 connection, and that's because pin 1 goes to pin 1, pin 2 goes to pin 2, pin 3 to pin 3, pin 4 to 4, 5, and so on. You get the idea. This is called a straight-through connection. And if I go back to the slide I did on the telephone modem, remember these DCEs over a single line, these DCEs are responsible for communicating full duplex, where you had a carrier that was taking data this direction at the same time a carrier that was taking data this direction. And because of that, you essentially had what was called a transmit-receive crossover. You had it such that a signal leaving here on transmit data would end up being interpreted by the receive data on the other end. So you had a transmit-receive crossover. TX here ending up on receive here, and TX here ending up on receive here. So that data was this direction, and that direction at the same time, giving you a full duplex. So when it comes to this connection for RS-232 between a terminal and a modem, it was the modems, or the DCEs, that are looking after a transmit-receive crossover over the data channel. And in the telephone modem, it was frequency division. When it comes to fiber optic, it's a separate fiber optic line for transmit and receive to give you full duplex. But it's always the DCEs that are looking after a transmit-receive crossover. And so the RS-232 lines are straight through. So that's a straight through example. Now, what we're looking at is the example of null modem. So this is the type of connection we're going to be configuring and connecting in the lab all the time, is a null modem connection. And that's where we connect two DTEs together directly using RS-232. So you're going to connect a PC to a PC in lab 1. So that is, without the use of a modem, you're going to be communicating between two PCs, right, over RS-232. You could communicate from a PC to a PLC, right, over RS-232. That would be a null modem connection. You're not using a modem in that connection. So the list goes on. You could be PC to RTU, PC to smart relay or protection relay, like we're going to do in our lab 2 and 3, and so on. But the idea being is there's no modem in this connection, no DCE. So it's direct communications without DCEs. It's terminal to terminal, PC to PC, and so on. Because we're missing the DCEs, because we're missing the modems, remember, it was the modems that were doing the transmit and receive crossover. So in order to get transmit receive crossover, that we do need for sure to be able to communicate between these two terminals, we have to build it into the cable. So that's how come for a null modem connection, that is without modems, you need to use a crossover cable. So it means for a 9-pin connection, pin 2 and 3 are crossed over. So within the cable, you have a 2-3 crossover. And for pin 5, remember, we're just going to forget about 25 pin. You know it exists. But the signal ground for a 9-pin is pin 5. So you have a straight through on pin 5, providing signal ground continuity from one terminal to the other. And then you have a crossover for transmit and receive, so that the data leaving one end will end up on the receive of the other, and you don't have it you don't have a collision on the data line. So this is what's called a null modem connection, or a crossover cable connection, and this is the type of connection we'll be doing in the lab all the time. So don't be confused by these diagrams. It's kind of funny because it's the straight through that looks like a crossover, and it's the crossover that looks like a straight through. So just be very look specifically at the pin numbers. So this is pin 2 connected straight through to pin 2. This is pin 3 connected straight through to pin 3. And that being the case, this would be used for a DTE to a DCE. So that's going to be used between a terminal and a modem. But over here, you've got pin 3 going through to pin 2 as a crossover, pin 2 going to pin 3 here as a crossover, and then of course you've got that straight through signal ground. This would be what would be required when you want to communicate between two DTEs, a DTE to a DTE. Okay? So just to look at some RS-232 specifications, when we look at this table, this is the maximum baud rate, maximum official baud rate for RS-232. And this is the maximum cabling distance for RS-232. Now, if you look anywhere for specifications, you'll always find they're based on worst case scenarios. So why do I say that? Well, because of the technology that's improved for the manufacturing of data cables, because of devices that are better at processing data over a data line. You could really say that this is a under-spec'd value, that with devices and cables nowadays you could take this far beyond that. But this is still officially the maximum data rate of 19.2 for a baud rate and the maximum cabling distance. So that being said, that means that one of our quiz questions is always going to be, what's the maximum cabling distance for RS-232? And the answer will be 50 feet or 15 meters. So that being said, notice how this table does indicate that with lower baud rates, like say 4,800 baud, you can go to 1,000 feet. This is really just demonstrating or letting you know that with lower baud rates you can extend that distance. But at the end of the day, I kind of give this analogy. Let's suppose you were in charge of an RS-232 node or section of your substation network, and you installed it based on the fact the order came out for 4,800 baud, and you knew you could extend to a device in the substation yard at say 500 feet away. So you're going, yeah, I'm good at 4,800 baud. But then later on, a change order comes out to change all drops within your network on RS-232 at all your substations to 19.2. Well, what's happened now, you can't just go in there and reprogram that connection to 19.2 and expect it to work, because you strung those drops to 500 feet. And so always when you you design and work with outside of specification and code is obviously when you can get into trouble. So I'm just kind of using that as an example. No doubt you can take RS-232, and you will find RS-232 taken beyond these limits, but that's just something to understand or be aware of when it comes to this. And again, when it comes to our official spec and asking the quiz question, this is the answer: maximum 50 feet or 15 meters. Okay, so RS-45 is the newer RS-232. I guess we could put it that way. It's still an asynchronous serial data connection, just like RS-232, but it uses a different type of signaling. When it comes to RS-232, RS-232 uses a reference to ground signaling. It's either a high or a low voltage reference to ground. When it comes to RS-45, it's a type of signaling called differential signaling. So notice how it says differential signaling for RS-45. Well, because we have differential signaling and we've changed the design of the physical protocol somewhat for RS-45, it brings to us several advantages. Okay, so first of all, when we're talking about RS-232, notice how it says number of drivers and number of receivers is 1 each. So that means that RS-232 is strictly point-to-point. You can always only have one RS-232 device transmitting to another one and vice versa. It's strictly point-to-point. Because of the newer design of 45 and the fact that it's differential signaling, you can have a number of advantages for 45, and one of them being that it's not strictly point-to-point, it's a multi-point where you can have 32 different devices connected on one node. Okay, now because of that, it means that the full duplex capabilities of point-to-point for RS-232 are gone, and you're limited to only half duplex. But it's still very efficient because of the speeds. Look at the speed we're capable of. Instead of just 20 kilobits per second, we've got 35 megabits per second. And look at the distance. And this is really all related to this parameter right here, the fact that it uses differential signaling. So even though we don't do any labs involving RS-485 in the lab, you can understand it's the same type of asynchronous serial connection, but whenever you're looking to multi-drop, you would want to go with RS-485, or if you wanted to even extend your distance officially, look at that distance for 485. 1.2 kilometers is the maximum cabling distance. Okay, so where does that really put us? Well, in terms of this course, what we want to do is understand that 485 has a number of advantages, and you could use this table or anything else to list the advantages, but we're very specific in terms, I guess, of our curriculum and our quiz question. We say, what are the 3 advantages of 485 over 232? So in a multiple choice question, you would get this, and you would look to find faster data rates or faster speeds. There's 1. 2 would be can be multi-dropped. So that's an advantage. It can be multi-dropped. And then 3 would be longer cable distance. So that's what we summarize as the 3 advantages of 485 over 232. Faster data rates, can be multi-dropped, and has longer cabling distances, maximum cabling distances. So when it comes to RS-232, it's strictly point-to-point. Notice how we're seeing a crossover here, transmit to receive, receive to transmit. We've got a crossover cable there, and that's of course capable of full duplex because it's got separate data channels. Here in the RS-45 we have a multi-dropped or bus connection, but the data channels are in common. We don't have a separate data channel for transmit and receive. So notice how one of them in this example is the host, and it's the only one transmitting, and we have a multi-dropped receiving of each one of these devices, right? Now, of course, this would be half duplex. A device, once this guy is done transmitting, let's say device number 2 could become the host and then do the transmitting and the others the receiving. So that's a half duplex, right? That's a half duplex connection. Now there is full duplex RS-485, but if there is, that means you're not 2-wire anymore. If you have a 4-wire system, you can do full duplex. Okay, so if you have 4-wire, you can actually have RS-45 full duplex. Okay, just picking up where we left off here. Here's where we're going to look at modems specifically, and what are the different types of modulation techniques that can be used on modems. Now, the first thing to understand with the modem, of course, it's the DCE. It's the data communications equipment. And so its job is to take the digital information that's found as highs and lows, ones and zeros from the terminal, because we know that's the signal that the terminal always offers up for a transmit or is looking to receive. That takes that electrical signal and changes it to a signal that's suitable for the data channel. So that's the job of the DCE. And in most cases, a DCE takes on the name modem. And so it's impressing upon the analog signal the information, the ones and zeros. And when it does in the transmit direction, it's what's called modulating the carrier. And when it's receiving the signal as the receiver, it's demodulating the signal. So in the transmit direction, it's impressing the information upon the carrier. In the receive direction, it's decoding or removing the information from the modulated carrier and delivering the high-low signal to the receiving terminal. And so that's called a modulator-demodulator, or it's shortened to give you the term modem. And that's where the term modem comes from, modulator-demodulator. So the modem's job is to act as the DCE, right? So it's the DCE in the system. So in the transmit direction, like we said, modulation, receive direction, demod. Okay, just gonna... Okay, so there's really 4 modulation techniques that we're gonna look at that can be employed by a modem. And this is really specific to datacom, but when you think about a couple of the examples like the FM and AM example that we're talking about here, it's the same thing with analog carriers for analog radio, like what you listen to in your vehicle. A lot of times it's digital radio these days, but if you just think about the average car radio, it has both analog AM or amplitude modulation stations, frequencies it can tune, as well as FM. So when it comes to these techniques, we're going to look at frequency shift keying, often called FSK, which is a form of frequency modulation. Wouldn't matter which one you called it. Amplitude shift keying, or ASK, corresponding to amplitude modulation. Phase shift keying, PSK, or PM, or phase modulation. And then a very special one at the end here called Comm. And we'll see what's specific about Comm. If we look at FSK, you can see the DTE signal on top here. This is the DTE signal. Okay, so I just had an issue with my writing device here. So I got it going, and we're looking at FSK, which is a form of frequency modulation. If we look up here on the top, this signal that you see here, remember, is the standard DTE or terminal signal, right? We know that all terminals, whether they're transmitting or receiving, are going to be either transmitting or receiving this electrical signal, highs and lows representing zeros and ones. That's where the information is. If we look at how that's modulating a carrier, notice how we have an analog signal, digital signal on top, an analog signal here. That analog signal is being modulated by frequency modulation for a low frequency corresponding to a 0, a higher frequency corresponding to a 1, and it's shifting the carrier between those two frequencies to represent 0 and 1. That's what's called frequency modulation. Notice how the amplitude of the carrier never changes, and there's no information contained in amplitude changes. Part of a natural transmission of this carrier would be fluctuations in the amplitude, but because the modulation is frequency, the amplitude changes are ignored and they're not considered. So amplitude remains the same, frequency changes with the information. So that's FSK. So then when it comes to ASK, you can clearly see that in this case, it's the amplitude that's changing, right? So notice how amplitude's changing, and we have amplitude 1, amplitude 2. If it's amplitude 1, most likely it's a 0, amplitude 2, a 1, and that's where you have the zeros and the ones contained in the amplitude changes of the carrier. Now in this case, you're just shifting between two amplitudes, two values of that carrier's voltage level or of its deflection. And so one thing to note is if this is a AM radio station and it's analog, then these are it doesn't shift between two amplitudes. The amplitude or the envelope of the carrier is representing the voice or the music or stuff like that. And this is really how come an AM station sounds so much more noisy than an FM station, is because the noise that's introduced is interpreted as information and then decoded by the receiver, so you're going to hear any noise in the connection. Whereas for FM, you don't hear it. And if you listen to a radio station of AM to FM, you can clearly hear the difference in the noise floor or the noise level from that signal. So that's AM or ASK. Now if we look at PSK, what we have is a shift in the phase. So it's the the phase that shifts relative to a reference, and most likely this would all be referenced to probably a power signal to know what the phase shift was and to use that phase shift to determine a 0 or a 1. Notice how essentially with phase shift what you've got is shifting through, say, a 90-degree shift from a reference, and how that actually allows you to come up with more combinations than just a shifting of between two frequencies or two amplitudes. You could actually shift through 4 phases of 90 degrees and essentially start to pack in more bandwidth into the same carrier than you could with just amplitude or frequency. I don't know if that's kind of making sense to you, but that's really part of what's going on here. Is phase shift modulation allowed us to pack more bandwidth or more data into the same bandwidth, and then we'll take it even a step further for the next modulation technique. But this is called phase, or PSK. Here's the one that's really allowed high-speed data connections over simple copper connections. And when it comes to TELUS and their DSL connections from maybe, I don't know, a decade ago or maybe a little bit more, it was this modulation technique of Comm that really allowed them to maximize their data throughput for just a twisted pair of copper like a regular telephone line. Before that time, you know, cable service providers like Shaw and things like that had a big advantage over places like TELUS because of the fact that they were working with coaxial cable and the greater speeds they could deliver. But once this came out and the techniques were all you know, perfected, and we had DSL modems and things like that, we could really pack a lot of high-speed data into just a simple copper connection. How's it done? Well, it's combining 2 modulation techniques into one. So that's amplitude and phase. So we have 2 different amplitudes. We combine that with a phase shift of 90 degrees, and that gives you like 8 different combinations for a single phase and amplitude, right? So a certain phase coupled with a certain amplitude gives you a 1-0 combination. So like I said, this really opened the door to high speed over twisted pair. And so just to be kind of aware of how a question would come up about these modulation techniques, the common question from our curriculum is, which one of the modulation techniques allows the greatest data throughput for a given channel bandwidth? So assuming all things being equal, you have a certain bandwidth for a connection, which modulation technique would allow you to get the greatest data throughput? And the answer, of course, is Comm here. And further, the question may be, what 2 modulation techniques does Comm combine? And the answer would be amplitude and phase. Okay. So now we just look at some transmission mediums. And again, this is very like low level introductory, but it gives you the idea. At least I think it does. So first thing we're looking at is any copper connection. Copper connections would be a twisted pair regular telephone or plain old telephone line. And that's a technical term, plain old telephone line. And places that would offer that are your telephone companies like TELUS. Nowadays, TELUS is moving away from twisted copper and traditional telephone lines to move everything to data and voice over IP and all that kind of stuff. But you know, originally, and there's still some out there, is twisted pair. The other day when I got internet connected to my home, I'm still on twisted pair here until they come around and throw fiber optic in for, you know, for data over fiber. So what do we generally have? Poor bandwidth and single loss due to resistance, capacitance, and inductive effects, like we talked about. It's got limited distance for high data speeds like internet speed or Ethernet speeds, but of course, Comm is what really allowed oops, sorry for being messy there. Comm is what really allowed this to still be a viable data connection. So then you've got your coaxial cable. Now when it comes to coaxial cable was used for delivering cable TV and satellite TV and all that kind of stuff, where there's a really huge requirement for bandwidth or frequency range. And because coaxial cable has that characteristic, by the way it's constructed to minimize capacitive and inductive losses, it's always been a high bandwidth connection for delivering data. The only thing about coaxial cable networks like Shaw's is they don't have a dedicated line back to a central office like TELUS does. So for TELUS, because they can advantage Comm and twisted pair, and the fact they have a dedicated line back to the central office, so that means at the central office, I'm going to call this CO, they can have a main pipe connection as a data trunk. So with a data trunk leaving the CO, they can move huge amounts of data, say over fiber or one of those synchronous data links that we talked about, and that each one of their subscribers is a separate twisted pair drop to the CO, to the central office. So you can see they can maintain a higher level of bandwidth, limited only to whatever that connection is that they have to the CO. Now when it comes to a coaxial cable, they have essentially a splitter, right? So this is a splitter in your neighborhood, so that when you don't have a line all the way back to Shaw's COs, you have all these coaxial cables coming into essentially a splitter or a bridge. And what happens is every time one guy goes on, so this is the first guy onto that splitter to receive data and move data, they're operating at a huge speed, greater than even could be provided by TELUS. But as soon as number 2 subscriber comes on, this becomes a high traffic area, and you can imagine number 3 in your neighborhood, number 4, just to give you the idea. Every time somebody else comes on here, this becomes a collision zone, and it drops traffic. Think about it like a roundabout. As soon as we've got more people running around the roundabout, it means that there's less traffic moving, or each individual has it can move, it moves slower, if that makes sense. I can always answer more questions there. So then we're talking about a fiber connection. Of course, fiber connection is huge bandwidth. You can't find DCEs or terminals that could even handle the bandwidth of fiber optic. It's, for lack of a better term, you could say it's essentially infinite bandwidth because of the frequency of light. So put it this way, in a data connection that's fiber, that's never the limiting factor for moving data. It's always the terminals or the DCEs. So in this, we're just showing the idea of a light pulse being the light on or off, being pulsed down the fiber optic cable. These would be your DCEs, right? Because remember, they are changing the signal from the source as a terminal, as a DTE. It's changing the signal from a high-low signal to a signal, in this case, which is light, appropriate for the data channel. So here's the data channel, right, which is the fiber optic link. And then, of course, here we're being demoded. So we're demodulating the light. We're demodulating the light in order to give us our terminal signal here of a high-low signal. Okay. So what really do these cables look like? Well, one thing you may not know is when somebody says, oh, here I've got a spool of fiber optic cable, in most cases it's not a single cable. It's many fibers within one sheath, right? And so that's the case we have here. Fiber optic cable with many fibers within one sheath. So you usually have, say, redundant fibers that can be used if you have a fracture or a breakage. Other fibers that can be used for multiple channels of communication and so on. So that's just something to be aware of. When you see a cable, a lot of times there's many fibers in it. Now, in this case, if we look at a single fiber, the way the single fiber is constructed is like this: an outer cladding, essentially a optical sheath that runs around inside the cladding, and then the actual fiber itself, the glass fiber of where the light runs down. When you look over here, notice how this says a duplex patch lead. This means this is now capable of full duplex fiber. And if you have a full duplex fiber connection, what it means is you need a separate path for both, for one direction, right? So if I had data, if this was the transmit side, data would enter this direction and you would receive data on this cable. So that would make it a full duplex fiber connection. If you only see one fiber cable entering a device, then it's a half duplex. But again, because of the speed of fiber, you're not finding half duplex is a limiting factor. But a lot of times they have a full duplex system for other reasons too, and one of them being reliability and issues like that. So full duplex would have two cables. So here's just an animation of two different fiber cable constructions, right? And so this would be a DCE here transmitting to a DC here, and it's obviously a fiber optic modem. Now the thing is, there's two types of fiber systems. There's the single mode fiber system and the multi-mode fiber system. If we look at this animation here, you see there's clearly one example that's showing on the top here of a straight shot straight down the barrel, if you want to call it that, or the fiber of this cable. So on the top here, this would be what's called the single mode DCE. That's a single mode. Down at the bottom here, this one is the multi-mode. So the multi-mode transmitter is essentially a scatter and bounce down the fiber or the glass strand. The single mode is a straight shot down. Now, as you can imagine, the single mode is far more efficient than the multi-mode because doesn't have the losses of the bounce and scatter. It's a different cable. It's a different transmitter, it's a different receiver than a multi-mode cable with a multi-mode transmitter and a multi-mode receiver. So notice how a single mode, there's only one path for the beam of light, therefore more speed, more distance, and bandwidth. So the bandwidth is greater for single mode. The distance between fiber optic repeaters is farther, and of course there's more speed. So if you had if you were looking at a synchronous data trunk from, say, here to Edmonton, I mean, the most logical solution is going to be single mode. You're going to have less repeaters and it'd be most efficient. For places like, say, running a fiber network around campus at SAIT or something like that, multi-mode would be the economical way to do that, because you know, the fact that you can't go 75 kilometers between repeaters is not an issue, whereas, you know, for the long distance it is. So and furthermore, the bend radius to get around buildings and corners and rooms and ceilings and cable trays is less with multi-mode as well. So that's single mode versus multi-mode. So the benefits of fiber in general are its huge bandwidth, yes, beyond equipment limitations. Very low signal attenuation, loss of light is not like an electrical signal. There's built-in security. You can't just have somebody come along and clip on a speaker and hear what's being said or anything. It's a light carrier. It has low error rates, very immune to noise and things like that. Very immune to EMI and RFI. So EMI stands for electromagnetic interference and radio frequency interference. It's lighter and smaller than copper cables. There's total isolation. It's safe for hazardous locations and is intrinsically safe. And no crosstalk between cables and cable trays and conduits. So if you can afford it, it's obviously a big deal. And protection networks are using fiber optic networks a lot too, because they'll use a fiber optic cable to detect arc flash, so that when they have an arc flash and the light from the arc flash travels down the fiber optic cable, it can trip that protection device in a much faster trip time than something like an electrical detection or 4 to 20 or something like that. So the last thing we're going to talk about is radio, guys. And I have a fair bit of experience in radio with a bunch of wireless communications work I did for both SCADA and voice and all that in my previous experience. And one thing I can say that's probably from that experience that's the biggest kind of piece of advice I would give is there's a reason why we're showing this radio spectrum like we are right now and breaking it down into different bands like we are. And that's because we need to understand is that characteristics and things of all these different bands is not equal. There's certain characteristics that you would leverage for, say, VHF over UHF. There's certainly a huge difference in the wavelength of a very low frequency to a very high frequency. Look at that, 30 kilometers and 3 meters, huge difference. And it's things like that that change the size of anything like a resonator or a duplexer or an antenna. Back in the old days, as an example, cell phones came out at 800 megahertz. And at 800 megahertz, you had a much bigger cell phone, a much bigger antenna, and things like that. Nowadays, with the gigahertz frequencies for cell phones, you can put them in a much smaller package, have much smaller antennas and things like that. So it's all relative to the wavelength of the radio frequency. And I think that's something that's really important to point out. And furthermore, the propagation through free space is different even between two bands. So let me give you an example. If you were looking at communicating with a tower up on a hill in Calgary, VHF would be a better means or ways of communicating to the tower and over to somebody on the other side of the hill than UHF. And that's because the free space losses on UHF are much higher than VHF. Whereas UHF, being a shorter wavelength, is a better solution for something like a building or a factory where you want to communicate within those tighter spaces and around corners and things like that. So those are just examples where you need to be aware that not all these bands are created equal as far as radio goes. And that's probably the primary thing I would point out when we're looking at this. Radio is a wireless device that transmits or receives its information as electromagnetic wave. We have a transmitter or a receiver, or we have a combination of a transmitter and a receiver. For, say, a full duplex radio link would be a transceiver. It would be able to transmit and receive. And if it could do that simultaneously, it'd be full duplex. And if it was a take your term, it would be half duplex. But you get the idea. So the same modulation techniques that we talked about for a modem would be the case for a radio, because remember, a radio is actually another DCE, even though it's not taking on the name modem or DCE. It's taking a high and low signal from a terminal and modulating a radio frequency carrier. And that radio frequency carrier could be in any of the bands that we looked at. It could be VHF, UHF, extra high frequency, medium frequency, whatever. But the propagation and that has to be properly designed to work effectively for wireless. So just a simple little block diagram of what any receiving radio would look like would be to have an antenna, to have a way of tuning that antenna out of the, or tuning the frequencies the antenna is collecting out of the spectrum. So that means if you've got a wide bandwidth like this, right, and you want to select a certain frequency, you're going to have a tuner to tune in that frequency, right? So if this is frequency up here, you want a specific frequency, you're going to use a tuner to tune in that frequency. So you're going to have a tuner and then a, what's it called, a detector. So that's essentially a demodulator. So this is going to be a demodulator. That's what this detector is going to do. And then of course once you have your signal, in this case because this is an audio radio, it's going to amplify and send it to a speaker. In our case for a digital or a datacom, it wouldn't be a speaker, it'd be an amplifier heading to a DTE, right? A terminal, because we'd have a terminal signal. So what are the main things we want to point out is that antennas and all the antenna gear really has everything to do with wavelength. So it means that the lower frequency that has a longer wavelength is going to have a bigger antenna, it's going to have a bigger duplexer, it's going to have a bigger resonator. Anything that has to do with the actual RF signal itself is going to be physically bigger for longer wave or for lower frequencies. And I made that mistake myself when I did my first job that I spec'd out for a mountaintop repeater. I didn't take into consideration it had to go into a very small shelter, and I engineered the whole thing for a lower VHF frequency, and sure enough, when I actually received the gear, I realized it wasn't going to fit in the communications shelter, so I had to re-engineer the whole thing. But I learned from my mistakes, and that's why I'm trying to just kind of tell you guys or warn you that don't be just thinking this whole thing is all just, hey, it's radio. You have to take into consideration the different bands, the different wavelengths, and things like that when you engineer it or design it or put it together. So just want to mention that. Yeah, so this is just a reminder of what I just said. And really, this is it, guys. This is the end of this presentation. I'll get this published and put into, coupled with the other parts of this presentation, and get it on YouTube and get it up there so you guys can watch it from beginning to end. So yeah, okay, that's it for this one, guys.